So today I'm going to be talking more about, we're going to start talking about enthalpy. Let me take a look at the schedule here. All right. So we'll talk about enthalpy some for a few days here, and then after that, we'll talk about adiabatic changes, and that will cover a lot of the types of changes that we'll go over in this class in terms of constant pressure, constant volume, constant temperature, and adiabatic. Right. And most likely what will happen is we'll end up getting to cover everything until we get to topic 12 here, entropy, before the exam on September 28th. Okay. But yeah, so before we kind of get going, any questions people have? Oh, all right. So then I guess let's get started talking about enthalpy, right? So, right, we talked before how at constant volume, right, that the amount of heat transferred at constant volume, assuming no extra work, right, is directly equal to our internal energy, right? We got that from just the first law of thermodynamics and the fact that at constant volume, no work is being done. Okay. Right? And what we'll talk about today is the fact that under constant pressure conditions, as well as some extra conditions, right, that the heat transferred under those conditions is going to be equal to a quantity we define as the enthalpy. Okay? Right? So there's kind of the similar relationship between delta U, delta H, and heat transferred under certain conditions. Okay? And so as we get there, right, first, what is the actual definition of enthalpy? What enthalpy is defined as? Enthalpy equals what? Related with quantities we've talked about already in this class. A internal energy plus what? Pressure is involved there, and what else?
Would it be volume?
Yes, volume. Thank you. H equals U plus PV. Right. So as just a reminder, right, because of kind of the changes that are going on with the university and right, we have lecture videos to review these topics, these concepts, right, and lecture notes that are posted online well before we have these classes for you guys to look at, review, take notes on, read the book, right, before classes, right, and then in class here, my goal is to highlight some of the points that are involved in the textbook, in the lecture notes, right, and to review those things, and then to spend a lot of time doing example problems and working through problems together as a class, right? And so please check out that stuff before we talk about it in class, right? So what are some of the properties of enthalpy? If you had to guess, based off of enthalpy having similar types of relationships with internal energy, what would potentially be some of the properties? Do you think it will be intensive or extensive? Say that again? Yeah, extensive, right? Oh, what is that? Right, it's going to be extensive, right? The more stuff you have, the more enthalpy that thing has, right? Right. What else? I think it will be a path-dependent function or a path-independent function. It will be path-independent or state function. What is going on with formatting? And then what else? This third property has nothing to do with, is not related. Well, yeah, I guess in some ways you could say it's related with internal energy, but anyone have any idea what this third property of enthalpy is?
That the absolute value of H is undetermined.
Yeah, right. So enthalpy has no absolute value, if you will, right? No determined absolute value, right? That internal energy, there is a zero internal energy, right? I can't have negative internal energy, right? I can't have negative kinetic energy or something like that, right? My internal energy has an absolute zero, right? That you'd get at absolute 0 Kelvin, right? 0 Kelvin, you got zero internal energy, right? Enthalpy, on the other hand, does not have some absolute like zero value, right? There's no absolute value, predefined value for enthalpy, right? As there is for internal energy. Again, I could measure the kinetic energy, measure the potential energy of my substance, and tell you exactly what its internal energy is, right? Enthalpy doesn't have as easily well-defined value, doesn't have an absolute like minimum, some absolute defined value, okay? And this will pop up later when we talk about enthalpies of reactions and things like that, right? And how we base off our enthalpies based off of enthalpy of formation reactions and talk and use Hess's law and other things of that nature, right? So that kind of the fact that enthalpy has no defined zero value will pop up again. Yeah, so those are the properties of enthalpy. It's an extensive function, it's a state function, and it has no absolute predetermined value. Okay? Right? And right, as we talked about, enthalpy can equal heat transferred under certain conditions, right? So what are the conditions required for this heat transfer to work? Under what conditions does Q delta H equal QP? Close. Yeah, constant pressure, right? So this has to be constant pressure, but there's also something else that needs to be true with respect to that pressure. Yeah, that has to be at mechanical equilibrium. Right? Right. During your change, right, you have to be at mechanical equilibrium. So it's not necessarily that you are at mechanical equilibrium at the very end. It's that while you're changing, you're at mechanical equilibrium. Okay. Right. Right, and then the one, kind of the given one that we always talk about is no extra work, right? are considering here is pressure volume work. Okay. Right. And under these conditions, right, then enthalpy change is equal to heat transfer. Okay. And so why we often talk about enthalpy in chemistry and not internal energy is because often in the lab, we're under these conditions, right? A chemical reaction takes place in the lab in some beaker. Usually that beaker is just an open beaker, open container, right? It's at mechanical equilibrium with the external pressure, right? There's no divider, there's nothing to keep it from being at mechanical equilibrium. And it's a constant pressure system because the pressure in your lab is constant, right? So you're at constant pressure at mechanical equilibrium, right? Assuming you're not doing some random crap to have some extra work, right? Which is not typically happening in typical chemical reactions, right? So we meet all of these conditions in lab, right? And so in lab, right, when we measure the heat that's been transferred from our chemical reaction, that's related with the enthalpy change in this chemical reaction, okay? And so again, that's why often we talk about enthalpy in chemistry, because we're typically under these kind of constant pressure conditions in the lab and not so much constant volume conditions. Yeah. Right. Again, you could argue that the volume of our lab is constant, okay, but the volume of your reaction is not held constant, right? Because you don't have, say, a closed container, right, that you're typically doing this reaction in, right? Where then if a gas is being formed, the pressure gets built up in the reaction and things of that nature, right? Right? If everything is taking place in, let's say, liquid phase, then and no gases are being generated or consumed, right? Then constant pressure, constant volume is going to be the exact same type of thing, right? But any gases are involved in that chemical reaction, right? We're typically under constant pressure conditions for those gases and not constant volume conditions. Okay? Questions so far? Now, if I do have a chemical reaction, right, that's taking place at some constant temperature, right, what is the relationship between the enthalpy and internal energy change for those conditions? So how does what's the relationship between delta H and delta U? Right, this relationship, right, related with RT times the change in number of gas molecules, okay? So that delta Ng is related with is the number of gas molecules that change, right, under those conditions. Okay? Right. Again, this assumes constant temperature. It's also assuming an ideal gas, right? I guess the other thing is, right, we're assuming ideal gases for this, okay? Right? But if you have a chemical reaction or phase change where you're changing the number of moles of gases at a constant temperature, okay, then that change in internal energy is related with the change in enthalpy by this equation, right? And we can kind of get that from, right, go back to this equation here, H equals U plus PV, right? The definition of enthalpy, right? Well, the change in enthalpy is equal to the change in internal energy plus the change in P times V. Well, for an ideal gas, P times V is just nRT, right? So that change in PV is just change in nRT. If temperature is constant, R is a constant, right? Then it's just that change in number of moles, and specifically the change in number of gas molecules, right? All right. So questions about kind of enthalpy so far. What is it? What's its relationships? Talk in more general in a minute about how we actually calculate enthalpy for a given process. But for here, do a quick kind of review of some things we talked about, right? For example, here work equals minus nRT ln v final over v initial, right? What conditions, assumptions underlie the above expression for work? Oh, wait, let's ignore answer thing. Right. It's mainly just, right, think about what conditions does 1 need to be true, 2 need to be true, 3 need to be true, 4 need to be true, 5 need to be true, and 6 need to be true, right? Which of those 6, could be all 6, could be just 1, could be none, right? Need to be true for that expression for work to be valid. Right, I'm doing this question here. I'll try to keep on doing things like this periodically in different lectures, okay? Because hopefully we, with practice, with doing homework, with doing example problems in class and things like that, be able to look at this question and be able to answer it fairly quickly, right? Because that's the type of thing that you'll need to be doing on an exam, right? Because on an exam, you'll have some question, right, about how we expand gas under certain conditions and things like that, right? How do you calculate work, right? You need to be able to identify, okay, this is how the changes were made. Based off of how the changes were made, this is the relevant equations for calculating work and things like that that I need to use. Oh, okay, yeah. I can do that real quick. Yeah. Force constant. So say that again. Reversible ideal gas and yeah, constant temperature. And while we didn't really talk about it when we first presented this equation, the number of moles also has to be constant, right? You can't, right? No phase changes, no chemical reactions, right? So yeah, so we need 1 constant moles, 2 constant temperature, 5 an ideal gas, and 6 for it to be reversible, right? Reversible means it's at mechanical equilibrium, and that is how we get that expression for work, okay? Does not need to be constant pressure, does not need to be constant volume, okay? Now actually no, you couldn't have a constant pressure. I'd say you could do it on constant pressure, but that's not true, right? If moles are constant, temperature is constant, then and volume is changing, then pressure better change, right? Like PV equals nRT, right? Like if volume's changing, something else also has to change. So it's got to either be moles, temperature, or pressure, right? So right, out of 1, 2, 3, and 4, only 2 of those can be constant at a time, right? For the others to be changing, right? But yeah, so 1, 2, 5, and 6 are the conditions that are needed for that expression to work, be valid, right? And so again, right, in the problem, you'll see something like, say, right, I have 5 moles of ideal gas that's expanded reversibly and isothermally from this volume to that volume, right? What is the work done, right? And given that sentence, right, we need to identify this is how I calculate how that work is done. Okay. Questions? Yep. No. The form, so I will, there's review days before the exam. On those review days, I highlight what equations you need to know. I know what equations will be given, but there will be some equations given, but yeah, not all. For example, let me go to the Canvas site real quick. So already on Canvas are some equations especially related with like entropy, enthalpy, work, internal energy, and so on. It's not sending thing. Will be two-step verification. There we go. Here. Files. All right. So for example, freeze that screen and let me go to Zoom here. Share that, right. So for example, say this table I have already on the Canvas website, you can look at, right, as a list of work, heat, internal energy, enthalpy, and entropy. Right, in the first exam, we won't be talking about entropy, so you don't need to worry about that, right? But as a list of equations you need to potentially use to calculate these values for different types of changes, right? Well, the nice thing is, as we've talked about with internal energy, and we'll talk about today with enthalpy, or it's a state function, right? There's only one equation that matters, right? This assumes, right, ideal gas, constant heat capacities, no chemical reactions. I guess I didn't put that there, right? But no chemical reactions or phase changes, okay, right? Right, work, you got a bunch of different equations depending on the type of problem, right? And then Q is typically just getting obtained from the first law of thermodynamics, right? But right, but there's kind of lists of this type of stuff. There's also right, another breakdown of equations for different things, internal energy, right, different approximations, right, equation we just talked about and we'll use today. Work, what are the assumptions for the different equations and things like that. If there are phase changes, chemical reactions, how would you calculate it? Right. No. Yeah. So the summaries of these things on Canvas as well, for reviewing for exams and things like that. But yeah. But yeah, you won't have equation sheets on exams and things of that nature, right? Because part of, right, I mean, the previous faculty member had you derive these equations on the exams. I don't feel like you knowing how to derive them is that important, but understanding when to use relevant formulas, relevant equations, and things like that is important, right? To be able to understand what's going on in a problem, interpret it, and know what is the correct equation to use is kind of, part of the information learned in this class, right? If you had a formula sheet where you could write out, okay, this condition you use this condition you use this, right? Then every problem is literally just plug and shove, right? And because you're told, you can look up, okay, this is the problem, this is the equations, I just plug in and shove, right? And that's what, again, fundamentally, a lot of the math of these problems is just plugging in and, solving for some unknown variable. But part of, this class is identifying when to use certain equations, right? How do I interpret my problem into the relevant set of equations that I need to solve for, right? And so, yeah, we don't have equation sheets and things like that, and it kind of defeats that purpose. So, all right. So if I do the combustion reaction of 1 mole of methane, right, what is the change in number of gas moles, that delta Ng, for that combustion reaction, assuming it goes to completion? I guess you can assume all the products are gases as well, right? Because it would change depending on whether or not everything's a gas or not. But yep. So I mean, like, yeah, assume CH4 is like your limiting reagent, right? And it's burnt to completion. And so we want to count all the gas molecules in your balanced chemical reaction for assuming everything is in the gas phase, that reaction. Does that kind of answer your question or not really?
No, so the equation is CH4 plus O2 to H2O plus CO2.
Yep.
So both sides have 3 moles of gas.
Yep.
So would it be 0, or would you not include the CO2?
So it would be 0. So yeah, so that is, so there you go. Right, so yeah, that is the answer, right, in this problem. It is 0, right? Because as was just stated, right, if you write out the balanced chemical reaction for the combustion of methane, you have CH4 gas plus 2 O2 gas going to CO2 gas plus 2 H2O gas, right? And this has a total of 3, right? Gas molecules are 3 moles, right? If we're burning this to completion, right, there's 1 mole here, right? There's got to be 2 moles here, right? And so that's forming 1 mole here and 2 moles here, right? So that's a total of 3 on the product side, right? So the change in number of gas moles is 0, right? Because they go from 3 to 3. Okay? Now, if water was in the liquid phase, then you'd go from 3 to 1, and then, you know, it'd be 2, right? Or negative 2 moles, right? But assuming water here is in the gas phase, which I didn't really state in the problem, but yeah, assuming it's in the gas phase, then it would be 3. But if it's liquid phase, then it would be 1, but, or negative 2, but yeah. That's really crappy looking through. So questions about this problem? All right. So for this reaction here, right, at a fixed temperature, what is the relationship that I would use to calculate delta H from a measured value of delta U, assuming all the gases behave ideally? So some D's, right, from both Zoom and in class here, right? So if we look at this, right, we have a total of 3 gas particles on the right, 1 on the left. So you get 3 minus 1 is the total change in the number of gas molecules, right? That's 2. So it would be, in fact, D here, 2 RT. Yeah. Questions about that? All right. I swore I moved that slide. I thought I had this slide. So we're going to do this one and we'll go over some examples, right? So want to talk briefly about H, its and some of the kind of definitions and heat capacity at constant pressure, right? So as we talked about last time with constant volume, right? The constant volume heat capacity was related with du, dA, or du, dt at constant volume, right? Constant pressure heat capacity is a very similar type of equation, but now it's a change in enthalpy, a change in temperature under constant pressure conditions, okay? Right, we can rewrite that equation again as just dH equals Cp dt, right? And so this is how I could calculate my enthalpy change for heating in a single phase, right? If Cp is constant with temperature, then I can just write this as delta H equals Cp delta T, right? Because if Cp is constant, right, the integral of dH is just delta H, integral of dt is just going to be delta T, right, from some initial final values, okay? And so I get delta H equals Cp delta T for constant temperature, okay? Or constant, sorry, not temperature. All right, thank you, Cardo and Derek. So I don't know if I'm clicking something, if the mic does something, I don't know. I don't know how that randomly happens, but yeah. So again, what I was saying, right, is that, right, this formula delta H equals Cp delta T, okay, is true for when Cp is constant, and will always treat Cp as constant unless explicitly told otherwise, okay? And then that, right, this formula down here is very useful, right, to relate the heat capacity at constant pressure to the heat capacity at constant volume for an ideal gas, right? Specifically here, these are the molar heat capacities, okay, right? If I didn't want to use the molar heat capacities, I would need to multiply R here by N, right? It'd be the number of moles times R plus CV equals CP. Okay? But yeah, okay. And we'll later on in a few weeks, we'll actually talk a lot more about that relationship between CP and CV and show where it comes from and how to derive it. But yeah, but for now, it's just kind of a given. Okay? So like internal energy, enthalpy here, assuming no right, phase changes, no chemical reactions, right? I'm just heating a single phase, okay? This is always what I can use to calculate the enthalpy change, right? Which will look somewhat familiar because right, I think in 1341, this is kind of what you're told, right? When you heat a substance, right, to calculate the heat transfer enthalpy change, right? Just like Cp delta T and stuff like that. I don't know if they specifically said Cp, the constant pressure heat capacity, or if they just said heat capacity, C delta T, but right, again, it's a very familiar form. Questions? back. Question here. I have a sample of a gas containing 3 moles of benzene in a fixed volume at 15 liters and 300 Kelvin. Right? I give this system 3.5 kilojoules of energy as heat to increase the temperature to 350 Kelvin. Right? I assume benzene behaves as a van der Waals gas with a constant, with constants A and B given. What is the work? Change in internal energy in the change in enthalpy. Oh, I didn't. All right. Right. So here I have kind of written down a bunch of just bits of information from what's written in the problem, right? My gas is treated as a van der Waals gas, so I know the equation of state is as such, right? I'm told I have 3 moles, right, of my gas. Told that it's a fixed volume container, right? So constant volume. I'm given the, constants for the van der Waals gas, A and B. Told that there's some amount of heat that's transferred, right, into the system, right? Since it's transferred into the system, for the system, Q is minus 3.5 kilojoules, right? And then I'm given that the temperature, or sorry, not negative, positive, it's transferred into the system, positive 3.5 kilojoules, right? And the temperature goes initially from 300 Kelvin to a final temperature of 350 Kelvin, okay? Right, so that's what we're told, right? And then we're asked, right, what is work? What is delta U? And what is delta H? Okay. So the first question, right, what is work for this problem? 0, right? There's no volume change, so work is equal to 0. Right, from our first law of thermodynamics, we know then delta U is equal to Q plus W. W0, so it's just equal to Q. And we were told, right, that Q here is just equal to 3.5 kilojoules. So that is our change in internal energy. Okay. And so the final question is, what is delta H? Right. What can we try to use to calculate delta H? What equations do we know for enthalpy? Yeah, delta PV, right? So yeah, so that is the equation that we're going to want to use, right? Because, for example, we know we can say potential calculate delta H as NCPM delta T. We're given delta T, we know number of moles, but we have no idea what the heat capacity is for this van der Waals again. Okay, so this isn't really going to work for us. We just don't have the information given that's needed to solve that, right? The equation where delta U was, or delta H is delta U plus delta N G RT, right? This assumes constant temperature, right? And some phase change or change in number of moles of gas, right? That equation doesn't work as well, right? But to get to this equation, right, that I just kind of X'd out, we use this definition, right? The definition of H is U plus PV, right? So change in H is equal to change in U plus a change in PV, okay? Well, right, we're told, oh, I forgot to write that down, right? The volume is fixed at 13 liters, I think it was. 15 liters, thank you, sorry. 15 liters. So I forgot to write down, right? The volume is 15 liters, right? That was the other bit of information given, right? So I know volume, I know temperature, right, and things, but I don't know pressure, okay? Now I can use, right, if I look, I have my equation of state, right? Again, I'll write that out down here. P equals nRT over V minus NB minus AN squared over V squared, right? V is constant, N is given, A and B are given, right? And temperature changes from initial 300 to final 350, right? So I can calculate my pressure here and calculate delta PV, right? So if I calculate my initial and final pressure, I can calculate P initial times V initial and P final times V final. Another way I can do this is I can use this equation to say if I multiply both sides by the volume, right? So I multiply volume over here, right? So multiply everything by volume, right? And then the change in PV is just the change in this quantity here, right? Which only temperature is changing on the right. So delta PV, right, is the same thing as NRV over V minus NB times delta T, because that's changing. And then this quantity on the right here, right, doesn't change at all. The volume's constant, N is constant, and A is constant, right? And so this is the only thing that's changing. Okay. So then I can plug in here as, what do we got here? So this is, N is 3, so 3. Ideal gas constant 0.08206. I'm going to put my units here, and we'll see why in a second. Liters atmospheres per Kelvin mole. Right? This is moles. Right? And then divided by, or times 15 liters. And then divided by 15 liters minus 3 moles times 0.3 liters per mole. And then I multiply all that by my change in temperature, which is just 350 minus 300, so 50 Kelvin. Okay. Right. And I'm writing out my units here, right, to notice the fact that when you cancel things out, you'll be left with liters atmospheres. Actually, you know what? So I don't know why I use this, right? I can actually use the other value of R here. Sorry, I should have just used that from the beginning, right? So you could do this using this value of R, but then you have to convert from liters atmospheres to joules. Or you can do this problem, right, by using 3 moles times 8.314 joules per Kelvin mole, right, times 15 liters over, 15 liters minus 3 moles times 0.3 liters per mole, right? And then all this times 50 Kelvin, okay? Because the kelvins cancel, mole cancels there, and then this liter unit cancels with the liters in the denominator. So your units work out to where you can just use the 8.314 joules per Kelvin mole value, right? And so you plug all this in, right? And that will give you what delta PV is, and I can plug that back in up here, right? To then get delta H from delta E. Questions? When you do that, don't have the numbers right, it's on my head right, but when you plug in for delta PV, right, you get 1.33 kilojoules, okay? So delta H is delta U plus delta PV, which is 3.5 kilojoules plus 1.33 kilojoules, or 4.83 kilojoules for delta H. Questions? All right. So which of the following relations is incorrect for the reversible isothermal expansion of an ideal gas? A, B, C, or D, or none of these, all 4 are correct. Anyone have any thoughts? So B here. The other ones. All right. So let's think about some of this stuff. So for work, how do I get work for reversible isothermal expansion of an ideal gas? Yes, A should be negative, right? Expansion for a reversible isothermal ideal gas is minus nRT ln V final over V initial. So A here needs to be negative. So this is incorrect. Okay. Now what about C and D? People feel those that's correct or incorrect for those guys? All right, so Derek here on Zoom thinks they're correct, right? And Derek would be correct, right? Because, right, again, delta H, delta U, I have a gas that I'm just expanding compression, right? No phase change, no chemical reaction, right? Delta H, delta U, right? R, N, C, P, M, delta T, and N, C, V, M, delta T. Don't care how I do it, don't care what's being done, just that's how I calculate it from a change in state. Isothermal means delta T equals 0. So both of these guys equal 0. Oh my gosh. Share that screen. Sorry. Like writing everything out. See this, this, this. I'm the only one looking at it. Right? Right? So delta H and delta U, right? Again, as long as there's no chemical reaction or no phase change, right? My heat capacities are constant. That's what I use, right? And if my heat capacities aren't constant, if temperature change is constant, those are still equal to 0, right? So delta H and delta U are still equal to 0 for an isothermal process, even if the heat capacities are not constant values, okay? Because it's still going to depend on some type of a temperature change, right? And if the temperature is not changing, then there's no change in enthalpy and internal energy, okay? Right? So, so again, for isothermal, delta H and delta U are always equal to 0. Okay. And then B here, right? What relationships do I have with Q and W? And might include something else.
Q plus W.
Yep. Q plus W is delta U. First law of thermodynamics always works, always true, always valid, right? So if delta U is equal to 0, then Q will just equal negative W. Okay. So isothermal expansions of an ideal gas are super simple problems. Basically, everything's 0 but Q and W, and they're just opposite signs of each other. So literally, you just got to calculate work, and you're good to go. Okay. And when we talk about entropy, entropy is almost the exact same thing as work. You just divide by temperature and blah, blah, blah. So it's very, very simple, very, very easy to calculate these things for reversible isothermal expansion. Okay. Yeah. So A is incorrect, and it's only incorrect just because it's missing the minus sign. It should be minus nRT ln V2 over V1, right? V final over V. All right. So question A through E here, which ones of these are going to be valid all the time, every time, anytime we certain? So can I always use equation A here, delta H equals delta U plus delta NG? No. Yeah, that's assuming constant temperature amongst other potential things, right? So A is definitely not always going to work. What about D here? Is that always what we can use to calculate work? No, right? If there's a change in temperature, right? If it's not reversible, if it's not an ideal gas, right? There's a lot of things that go into B, right? What about C? Delta U is equal to Q. No, right? Delta U is always equal to Q plus W, right? It's only equal to Q when W equals 0. So C is not always true, right? It's not valid under all circumstances. Then D, dH equals du plus PdV plus VdP. What is the definition of H? Yeah, right. H equals U plus PV. So if I just take the differential of that, right, I would get DH equals DU plus D like PV together, and then you just do the like product rule, chain rule, whatever the heck it's called, right, to get PdV plus VdP, right? So D, there is no assumptions being made. That is just the definition of H, and you're just taking the differential, right, looking at a small change in H, right? I can write that. Well, yeah. So right, this is looking at a small change in H, right? So some infinitesimal change in H is related with infinitesimal change in U, plus pressure times a small change in V, plus volume times a small change in pressure, right? And so D always works, right? And you could use D for any given problem and integrate out whatever you need to integrate, potentially solve for, say, enthalpy if you wanted, right? And then E here, is that true for all circumstances? No, right? That's assuming an ideal gas. So D here is the only one that really works all the time. Okay? So it's not a very helpful equation all the time, but it does technically work for any type of change. All right. So that slide we already went over. Okay. So I'm given CPM for a gas is 5½ R. What will the change in enthalpy be when 2 moles of that substance is heated from 298 Kelvin to 398? I guess, oh, I give you R's, never mind. How do I calculate delta H for the heating of a substance, right, in a single phase with a constant heat capacity? What do I need? Delta H equals what? Yeah, so that does work. What's another form of kind of how I'd calculate delta H, right? If I'm given a constant pressure heat capacity.
The specific heat under constant pressure times the change in temperature.
Yeah, so here I'm going to use the number of moles times CPM because we're given the molar. heat capacity, right, constant pressure times delta T. Right? Right, if so in this problem, I'm given the heat capacity at constant pressure, so I can definitely use this equation, right? We're given the change in temperature, given the number of moles, right? Yeah, NCPM delta T here, right? Right, as Derek's saying here, if you plug in the values given in this problem, you will get 4.16 kilojoules. Okay? So A here is the answer you'll get when you plug in, right, N CPM delta T, right? So it's going to be 5 halves times 8.314 times 100 divided by 1,000 to convert to kilojoules. You will get 4.16. Questions? Right? I have 1 mole of N2 expanding isothermally and reversibly, right? 298 Kelvin from 1 liter to 3 liters. Okay, assuming an ideal gas, what is the enthalpy change for this process? 0, right? Yeah. So, right, I have an ideal gas, I'm expanding it or compressing it isothermally, enthalpy is 0. Enthalpy change is 0, right? Delta T is 0, delta H has to be 0. Okay? So yeah, so this problem, don't need to even calculate anything. I already know delta H is equal to 0. Okay. Yeah, right. So here I'm saying, right, H state function. So I know delta H, I can just write as Cp delta T, right? No temperature change, no enthalpy change. Right. Question here, how would you calculate delta U for 3 moles of a monatomic ideal gas that is transformed from 10 liters and 250 Kelvin to 8 liters and 300 Kelvin? What equation would I use to calculate delta U? Yeah, so N CVM delta T. Yes, that is what we would want to use. We want to use moles times the molar heat capacity at constant volume times the change in temperature, right? Because delta U is a state function. So I don't care how I went from those initial conditions to final conditions, right? I can always use that form to calculate delta U, and that is what I would want to use to calculate. Okay? So we're doing some of these examples right now, going over some of these examples. And it's not a bad thing to do, right? The book has extra practice problems. You can look at things online and review questions on lecture notes and other things. Like it's not a bad thing to practice, especially later on when preparing for the exam, to just go over different problems. Don't necessarily calculate the final numbers. Just go over problems and try to identify what's going on in the problem and what equations do I need to use to solve for the things that are asked for in the problem, right? Right? And that's the main thing that we're trying to kind of learn here and identify and understand. That is given some question, right? What are the relevant equations that I need to use, right? And so again, like in this question, I'm calculating delta U. I know delta U is a state function, so I already know that I can either use, say, the first law of thermodynamics, Q plus W, or I could use, say, the fact that I just have an ideal gas that I'm heating, right? I can use in that CV delta T equation, okay, to get delta U, right? Because there's no phase change, no chemical reactions, okay? And so then all I need to identify is what is delta T, what is my heat capacity at constant volume, and what are my number of moles if I'm given the molar heat capacity. Great. Okay. questions so far about things we've talked about today, gone over, examples we've done? All right, if you actually calculate the value, right, you get 3/2, or 3 moles times 3/2 R times 50 with exchange temperature, which gives you 1,872 joules. All right. I have 0.425 moles of an ideal gas that expand against ambient pressure of 0.986 atmospheres from 5 liters to 10.6 liters at a constant temperature of 300 Kelvin. For this expansion, calculate W, Q, delta U, and delta H. All right. Right. So I have, right, some amount of gas that I'm expanding. Okay. I'm expanding against the ambient pressure of 0.986 atmospheres. So what type of expansion is that? A constant what? It's constant pressure expansion. My external pressure, right, is 0.986 atmospheres. Okay. Right. My volume change is from 5 liters, 10.6 liters, and I'm also doing this at a constant temperature here, which is at 300 Kelvin. Okay. Right. And the number of moles is 0.425. Right. So again, right, so writing out kind of the relevant information for this problem, right? It's constant pressure expansion, the external pressure, right? Constant external pressure expansion, right? External pressure is 0.986 atmospheres, constant temperature, right, 300 Kelvin, given some change in volume here, some number of moles, right? And I'm looking for W, Q, delta H, delta U, right? So again, let's think of the relevant potential equations for this type of a problem, right? Single phase problem, right? No chemical reactions and such, right? Delta U, we could use what? What are some of the relevant equations for delta U? Right, delta U, yeah, CV, delta T, yep. You could also say delta U is equal to Q plus W, right? First law of thermodynamics. Those two always going to work, right? Delta H. Very close to what we got here for delta U. CB delta T, right? Right. We could also try to relate delta H and delta U if we wanted to, right? Because it's constant temperature, right? Like delta H is delta U plus delta PV, right? If we wanted to try to use that, okay? Right, but we'll kind of focus on these ones here, right? In fact, it's related with delta T, temperature is constant, so we know both of these guys just equal 0, right? And then work for a constant pressure expansion is going to equal what? Negative P external delta V, right? Constant pressure expansion minus P external delta V, Okay. And then Q, right? How would I try to get Q for this process?
Negative.
Yeah, right. So it's negative work, right? Because we know the first law of thermodynamics, right? Always is going to be valid, right? So delta U is 0. So Q is just equal to negative work, which is just positive P delta V, P external delta V, right? And that for Q, that's basically almost always how I try to calculate Q and how I would suggest trying to get Q. Is worry about Q less and just use the first law of thermodynamics. Once you've gotten W and delta U, then worry about Q, right? Because delta U is easy, it's a state function. So we always kind of know how to do that. And then work, we know the relevant equations for work for different conditions, so we can always kind of get that. And then Q is just, the difference between those two guys, basically, right? All right, and so then to plug in for numbers, right, we would get work is minus 0.986 times my change in volume, right, which is 10.6 minus 5. And then if I convert this to joules, I'd have to multiply this by 101.325, right? And that would give me my work in joules, okay? To go back to the slides here, let me do this share screen so it pops up for Zoom, right? Go back to the slides, right? That work minus P external delta V ends up being negative 559 joules, which then means heat is just positive 559. Questions? Right. Again, I'm trying to, right, when doing these problems, kind of do the same type of steps every problem, right? Write out the relevant things that are given and the conditions that the problem is, like, that the change in this problem is undergoing, right? And then from there, try to identify what are the relevant equations for this problem, and then use the information given and those equations to then solve for the things that we need to solve, right? Right. So here, I have an unbalanced chemical reaction where I'm given the enthalpy change per mole of C6H6 for this reaction. Okay. Right. The question is, how much heat is released when I combust, right, burn up 13.02 grams of liquid benzene here. That's the molecule, right, C6H6, with its molecular weight of 78.11 grams per mole, or molar mass, right? Now, the other question is, what is delta U, assuming this takes place at a constant temperature of 800 Kelvin? So for the sake of time, let's just kind of talk about how we get this. So Derek here, right, is suggesting that delta U is potentially 0 in this case. So in this case, because we have a chemical reaction, even the temperature doesn't change, our internal energy and our enthalpy can change, right? Because for reactions, right, you're breaking and forming bonds, that's releasing energy, right, taking in energy, right? And so there's going to be an internal energy change because of that, right? When I'm not doing chemical reactions, right, and just heating and cooling things, right, the change in internal energy is related with the change in kinetic energy, which is related with the change in temperature, right? So that's why delta U and delta T are related for phase change, or for heating and cooling a substance, right? But when chemical reactions take place, then our potential energy is changing, right? Because I'm breaking bonds and things like that, okay? So yeah. But so for the heat released, how would I get to the heat released for this reaction? What would I use? Yeah, I would just take the enthalpy per mole here, right? This is the enthalpy change per mole of C6H6, right? And I convert my 13.02 grams of liquid benzene to moles of liquid benzene and just multiply delta H by the moles to get Q, right? Because again, under our typical reaction conditions, okay, we're under constant pressure and we're in mechanical equilibrium. So delta H and Q are equal to each other for most typical chemical reaction conditions and things like that, okay? So delta H and Q are going to be equal to each other for this reaction. And so, yeah, so I just get delta H multiplied by the number of moles that's in 13.02 grams of benzene, right? Then how would I calculate delta U? What would I be using? What equation would I use to get that? Yeah, right. So delta H is equal to the change in internal energy plus RT times the change in number of moles of gas, right? And so to solve for that, we'll just have to calculate the number of moles of gas, okay? So I'm kind of rushing through this a little bit for the sake of time, right? But again, if I convert the 13.02 grams of benzene to moles, right, by taking the mass and dividing it by that molar mass or weight, okay? And that will give you minus 550 or 44 kilojoules, right, is the enthalpy change, which is the heat that's released, right? That Q is also negative 544 kilojoules, right? And so we need to use delta H equals delta U plus delta or RT delta NG, okay? Right? If I write my balanced chemical reaction with just leaving 1 mole of C6H6, right, stoichiometric coefficient of 1 is C6H6, right? I get 15 halves, if you will, right, 15 over 2 moles of gas, forming 6 moles of gas here for CO2, right? Water, we're told in this problem, is a liquid, right? In the chemical reaction, while it's not balanced, right, we're given the phases, told, right, the water that's formed is a liquid, okay? So if you take the 6 gas molecules, right, minus 15.2, or 15 over 2, right, sorry, not 15.2, right? 15 halves, okay, just 7.5. So 6 minus 7.5 gives us minus 3 halves or minus 1.5, okay? And then I multiply that by the number of moles of benzene that's burned up, and that will give me the total number of moles of gas that have changed, okay? So 0.16 moles of benzene burnt. So my total change in gas is going to be minus 0.25. I dropped the minus on accident, okay? Shoot, and that carried through, right? So that's one thing, right? That should be minus, should be a negative 0.25, and this then should be minus. And so, okay, and so my final answer should be like it'll be like 3.4. No, 2.4. Okay. I think I changed that correctly. I don't know. You can double check that work. But you add 1.7 onto this side, be 3. Oh no, it wouldn't just be, no, I did not do that. There you go. That's what. Negative 540. Okay. So that is the change in internal energy for this process, right? Okay. We've essentially run out of time, but the last problem here, these are posted online as well, right, is calculating enthalpy when CP is not constant, right? So you basically just got to integrate CP, right, to evaluate things. Okay. But yeah, so if you have questions about stuff, I'm happy to answer them and things like that, right? Turn in your homework. Why don't you just leave it on the desk as you leave, on the back table, okay? Make sure your name is written on your homework. Yeah, so for those who are taking the class online, you should be able to submit it on Canvas. I think the time hasn't run out to submit it. I think it's like 12:30. Or sorry, yeah, 12:30. You should see an assignment on Canvas that allows you to submit it. Like if I go to Canvas here, we share that screen, right? So I'm on Canvas under assignments, right? You should see some assignment for you that's homework 1 online submission. Oh shoot, it just closed. I'll change that. Let me edit that right now. So you can have just a few more minutes to submit this online, right? But typically the due time is going to be by the end of the class period, when everyone else in class has to turn it in. I'll extend it an extra 20 minutes this time for those, right? But yeah, so it's due online, right? If you need to, you can email it to me. I prefer for you to submit it on Canvas so I don't have to like dig through my emails to try to find your homework assignment and stuff like that. But yeah, I prefer you submit it on Canvas. If you have to, you can always email it to me if you can't figure it out, right? But yeah, so if you're not able to figure out how to do that on Canvas, again, if I go to student view here, right, you should see something right on the bottom, you know, that like in terms of due dates or whatever. If you go to the home page course summary, you should see that online homework submission, and then you can click submit assignment, and then you know you can upload your file, right, to submit it, right, comments if you want to, and submit it, right. But again, if you aren't typically submitting things online, so Derek, I know you're normally in class, but weren't able to make it today, you can always email me that day, and that's fine. Again, if you need to email me your homework, that's okay. I prefer either in person or submit it through Canvas, just because then the homeworks are kind of located in like 2 specific places. But if you have to submit it via email, that's okay. Like I'll take it, I'll accept it. You know what I mean? I just don't want it to necessarily be like a regular thing. But if it happens every once in a while, that's more than fine. So yeah. Okay. So hopefully that kind of helped answer those questions. Any other questions? Those go on here. All right. So yeah, again, if you can't figure out how to submit that online in the next 20 minutes, then just email it to me, okay? And that will work, and we'll just work on making sure we figure out how to submit things online in the future. Okay? All right, so I'm going to close out the session and see you guys on Monday.